Okay, so if we're going to change gears today. We've been talking about the analytical solutions to the Schrodinger equation and all of those things with the particle in a box. And today we're going to do the same selection rules or derive the same selection rules using symmetry. Okay, so you'll see a dramatic difference in the reason we use symmetry in spectroscopy and also in the computational chemistry programs like Gaussian. They speed up whenever they're allowed to use symmetry. So we ended last time with a stick spectrum of an electron in a box, and we used this transition dipole moment integral results and the cosines and so on to determine the selection rules, delta n equals 1, 3, and 5, and so on. And so it was, four or so pages of calculus. As you guys are doing that for the lab, you'll see how tedious that is, all of those expansions and integration by parts and so on. But we're going to introduce even and odd functions today. So here's a couple of definitions, and I know they're written out for you, but maybe you want to rewrite them in your own handwriting, okay, as we're talking about this, so that you understand what I mean by f of minus x equals plus 1 times f of x and so on. Sometimes, even if you're just copying it, it's going through your eyes, bouncing around in your head, out your hand, and that's a great way to sort of cement things in your brain. Just looking at something doesn't necessarily get it to go inside, as you know, but actually writing it out. So that's why I say when you're reading something scientific, you need to have a pencil and a piece of paper so that an important point or a calculation, you want to do it in your own handwriting so you mentally can follow along. So at least write these two things down. An even function is symmetric around 0. And so let's look at this here. If we go to the left on this n equals 3 wave function, a certain distance, and then we go the same distance to the right, they have the same value. So that's the definition of an even function. You can also kind of see this with 0 in the middle, that this is like a mirror image. You see, if I put a mirror here, and I were to see the reflection of this left side in the mirror, it would look like the right side. Or if I took the inversion, like if I took all the negative x's and compared them to the positive x's, that would be an inversion through the 0, through the origin, and they're the same function. So all of those are different ways to say this top statement, this top statement of an even function. Now we'll see in a second this is very valuable if we can identify even and odd functions. Look at this one here, n equals 2. If I go left a certain distance, that's the opposite magnitude, opposite sign of going right the same distance. And so we could identify n equals 2 as an odd function. So now we're not talking about even and odd as divisible by 2 or not. Okay, this is a totally different meaning for the words even and odd. So get that into your head too. When we're talking about even and odd functions, we're talking about how they behave in space, not whether they're divisible by 2 or not. Okay, so if I'm talking about quantum numbers and I say even quantum numbers and odd quantum numbers, in that case I'm talking about whether it's divisible by 2. Okay, but if we're talking about functions, we're talking about this reflection symmetry or an inversion symmetry, and we're really talking about these characters. So even functions will have all these +1 characters in front of them. And when we see later on, when we talk about character tables, there'll be tables associated with various molecules. And the top row has all +1s. And all of the rows below that have at least 1 minus 1 in them. And so all the other rows are odd in some manner. And the top row is the only one that's even. Okay, so these characters will be really important here in a little bit. But for now, can you understand the difference between n equals 2 and n equals 3? n equals 2 is odd. You see the left and right side are opposite sign of each other. And then even though n equals 3 has some positive and negative parts to it, they're symmetric. So even the negative parts are the same and the positive parts are the same on the other side of 0. Okay, so that's an important concept. Here's why that's important. Because the integral over all space of an even function is non-zero. Oh, that's nice. Because we just did a whole bunch of integrals, and that was a pain. if we could identify even and odd functions, we could at least know whether those integrals are going to give us a non-zero result. And that's really helpful. Okay. And then the integral over all space of an odd function is 0. You can kind of see this on that n equals 2 function. If we were to integrate that function from the left to the right, we'd have some positive parts that would add up, and then those negative parts would cancel it back down to 0. So essentially for odd functions, the negative pieces and the positive pieces cancel each other out. They're the same area under that curve. Whereas an even function, you can have positive sections and negative sections, but the positive sections prevail. Or the negative sections prevail. They don't balance each other out, so they're non-zero. It could be negative, it could be positive, but we know it's non-zero. Okay, for an even function. And then we know the multiplication rules. So if I have a function times a function, if it's an even function times an even function, I know that the result is going to be even. And so we have these kinds of really 3 different rules. Even times even equals an even function. Even times an odd function equals an odd function. And then 2 odds will cancel each other out. So an odd function times another odd function will give you an even function. And these, you can kind of think of them in terms of their characters, right? We said that even functions were associated with a +1 character. So you can think of even as a +1 times a +1 gives a +1. And if odd functions are characterized by -1 in terms of their characters, then a +1 times a -1 gives a -1. So they do have that kind of +1, -1 character associated with the functions. And even the negative one. So -1 for an odd function, another -1 for another odd function gives us a +1. And so that odd character of those functions will cancel out. And that's actually what's happening when you take these functions. It's every result or every value, like the value of a function at -15, okay, times the value of the other function at -15. And if they're both positive, you're going to get a positive result. If one's positive, one's negative, you know, greater negative, you get a negative result. So you'll see the signs change in these functions, and it would be real tedious to do that by hand. But these rules will govern it. If you identify it as an even or an odd function, then you can use these multiplication rules to simplify things. So let's put this into practice. So let's think about this transition dipole moment integral we had for the wave function 1 going to wave function 2 for light interacting with it. And so let's first talk about this x-axis. If we had like f of x equal to x and we plot that, it's just going to be a diagonal line, right, going through the origin. Whereas as x goes, positive, say this is 15, then f of x equals 15, so that's 15 right there. And if it goes to -15, then down here it's going to be -15 because f of x equals x. So the x-axis is an odd function by our definitions, right? If I go left, it's negative. If I go right, it's positive by the same amount. So that's an odd function. So we can take this x piece right here. We know the symmetry. It's odd. We determined that the wave function 1 was even. You see here it's symmetric about this middle point. And then we determined that wave function 2 was odd, right? It's sort of anti-symmetric around that point. It changes sign when it goes past 0. And so we can look at this and we can use our multiplication table that we just made on the previous slide. And we typically do these from right to left, although it really doesn't matter. Odd times odd gives an even. So light times that wave function 2 is going to give us an even result. And so we just do these pairwise. We do odd times odd gives us an even. Next, we're going to do even times even here. Gives us an even function. And so what is this piece here? This is the integral over all space of an even function. So we're just tracking the symmetries of what's inside our integral. And so that means it's not equal to 0. So we know that that's an allowed transition. So this intensity of the transition from 1 to 2 is not equal to 0 because and this is what we say in quotes, allowed by symmetry. So we've done the symmetry analysis of this fundamental transition, and because we know the symmetries of the functions, then we can determine that this is an allowed transition. So that's really, really cool. Okay, in particular, this is where the math is saved. We don't know the intensity without doing the calculus, okay? But let me give everybody a post-it note here. All right, so with your post-it note, we're going to do this one on the right. So think about if you were assigned this by your TA, that you got quantum numbers 1 and 3. Okay, 1 and 3, and you're going to do these 4 pages of calculus only to get to the end and realize you have an even delta n and your cosines are going to cancel and you get a 0 result. Okay, but on your post-it note, go ahead and write out this piece right here. This 3x1 squared. Don't write the equals 0, right? Just put like question mark, equals question mark, right? And then we look up the symmetries of these functions. 1 is even, x is odd, and 3 is even. Okay, and then we have odd times even, which gives us odd. And you still put it in the angle brackets. And we have the even function number 3 times the odd. And when we multiply those two, we get an odd function. And now we have the integral over all space of an odd function, and that is equal to 0. So not allowed. And so you've taken 4 pages of calculus and we're able to get the answer on a post-it note. That is the power of symmetry. Yeah. So half the calculations now are done like that. And you could do all of the symmetries for these before you even get started. And then you could go in and do the specific cases for the other half and solve the transition dipole moment integral and get the intensities. Okay. So that's pretty cool. And that's why we like symmetry. Now, this is just one dimension. You could actually show both. You know, you could do the calculus by hand, and you're doing for your lab, and you could do it by symmetry. But when we get to bigger molecules, we can't do them by hand anymore. Okay, but I just wanted to show you this example where you do this really long calculus assignment in lab, and then today we do this on a post-it note, just to kind of show you the huge difference in the advantage that we get when we start looking at the symmetry of nature. It's really incredible. Okay, we can do this other one. Let's go ahead just for practice. We'll see that this one is non-zero, this overtone. So for n equals 4, we have an odd. and for X is odd, and for 1 is even. Odd times even is odd. And so then, this is screwed up my bracket. Okay, so then we have the integral over all space of an even function. And that's not equal to 0. So that will give a non-zero result. Now that's the weakness of symmetry, is we don't know the value. We can't tell you the magnitude of that peak, but we can tell you that it is allowed. So we can have overtones, but we don't know how strong they are. Okay, so to do the overtone calculation of the intensity, you have to get in and do the calculus. So this is allowed. Okay. So let's now start talking about symmetry. We're going to shift gears in the course and shift over to symmetry. And next week's lab is three-dimensional symmetry of molecules and point groups. So we call this group theory. So we're going to get into symmetry selection rules and all of the things associated with symmetry. We see this in nature here. Here's real world evidence of symmetry. We're talking about the particle in a box. It seems kind of fake, right? It's just an electron held on a 7-angstrom wire, and I mean, it's an okay example. But do we see symmetry in nature? Yes, right here in the infrared spectrum. So this would be the light coming off of a hot wire. It's emitting all of this light in the infrared. And then there's some specific light missing based upon species that are in the atmosphere, like CO2 and water. So what we're looking at is called a single beam spectrum, arbitrary single beam intensity. And it has that shape of a Blackbody radiator, because it is. It's just a hot ceramic coil. Can I get you to close that door? Somebody, please. And we have a couple of gaseous species here. We have CO2 and water. And look at how pretty. I mean, I see this as a spectroscopist and see this as pretty. These are equally spaced little peaks due to the rotation of CO2. And so CO2 looks very nice. We also have some, nice equally spaced rotational lines, and then this central peak, and it's symmetric on both sides and so on. And that's for CO2. It has 3 atoms, okay? And it's got a beautiful infrared spectrum. And look at water. I don't see any pattern in water at all. There's a lot of rotational lines in water, and it's a jumbled mess, both here and here. And the reason why CO2 is nice and water is ugly, can you come up with a reason? I mean, what do you think? Have you ever drawn the Lewis dot structure for these two? Yeah, so CO2 is linear, and water is bent. In fact, this is proof that water is bent. I mean, water has 3 atoms. It could be linear, okay? But it's those non-bonded pairs that give it this tetrahedral electronic structure that causes the hydrogens to be on 2 electron domains and 2 lone pairs, the sp3 hybridization and all of that. So because water has those 4 electron domains, it's a bent molecular structure. And that breaks the symmetry. So we're going to talk about what is it that makes CO2 more symmetric than water. It is, and we look at it and we kind of maybe intuit that it is, but what is it specifically that makes it more symmetric than water? And we see that it's definitely got ramifications in its spectroscopy. This is ugly, just so you know. Okay, and this is beautiful. I'll just say, nice. Okay, here's some more evidence. This is the automobile FTIR of automobile exhaust. Actually, it's from my motorcycle. Puts out quite a bit of CO because I just started it up. So that's carbon monoxide down here. Here's water. Here's this bump here is water. These are some CO2 bands, some CO2 here, and some CO2 here. But what's interesting is that one of the stretches in CO2 is only active in the Raman spectroscopy, and this stretch is only active in the IR spectroscopy. So that's, again, a ramification of symmetry, and we'll learn about why that is in the future. But here again, we see symmetry play a role in the real-world spectrum. So looking for symmetry, one-dimensional systems like the particle in a box, what we just did with the very wave function was pretty easy. We could do the same thing with a particle on a ring. That would be easy as well. On H atom, the radial wave function is lowercase easy. It still can be done, but it's not so easy. But all of the molecules are complicated. Determining the symmetry of the wave function for all of the molecules, we have to learn. We'll spend a couple of weeks trying to figure all of that out. Okay, it becomes easy with time, but you have to let yourself get it. This is where your ability in your mind to rotate things and to see sort of the depth in a drawing is really important. It's a skill that can be developed, though. This whole idea of I'm a auditory learner or a written learner or a visual learner or whatever is those are just like moderate strengths above the others. We have the ability to learn in all of those other ways, and so this is a very visual part of the course. And so just work at it and pair up with somebody so that you can ask questions and have them explain it to you a bunch of different ways. So all molecules are complicated. MO theory helps us understand diatomics. But then we apply MO theory to larger molecules. Some of the things transfer and other things don't. Okay, but symmetry helps us understand the symmetric molecules. And if it's an unsymmetric molecule, there might still be symmetry around each atom. So we could still talk about trigonal planar. We can still talk about octahedral, even though it might be in a huge thing, like hemoglobin, but that iron is still in a square planar arrangement. So there's symmetry around the iron, even though it's in an object or a molecule that's totally unsymmetric. So this is the point of this whole part of the course, this slide here. We want to know the selection rules for spectroscopy. Remember, this course isn't just about quantum mechanics, it's about spectroscopy and how to understand the data that you get in the lab. Okay, and so we really want to know the selection rules for spectroscopy. Why is a peak here and not here? Even though light could match this transition, for some reason there's no peak there. So the selection rules tell us that. And it's the direct product tables that allow us to determine those selection rules. But the direct product tables come from the character tables. And we'll explain all of these pieces. I'm just going over the outline right now. Where do the character tables come from? Well, they come from the point groups, but what do they allow us to do? The character tables are kind of like the Rosetta Stone. So, we uncover all these fantastic ruins in Egypt, and the pyramids and so on, and they have all these little symbols. And wouldn't it be nice to understand what they mean with the little snake and the bird and the little sun thing on top of this thing? And who knows what all that stuff means? Until we got the Rosetta Stone, we had a real hard time. So just like in this, you've got molecules and spectroscopy. Who knows how they're related? The character table tells you how they're related. Okay, so the character table is like the Rosetta Stone. They discovered this stone, and across the top they had hieroglyphics. And then in the middle they had more of like a handwritten script called Demotic script, and then the bottom they had ancient Greek. And they knew ancient Greek, and they knew a little bit about Demotic script. They had no idea about the hieroglyphics. And so the Rosetta Stone, because the same inscription was written in 3 different versions, they could compare the ancient Greek to the hieroglyphics. And they're like, now we know the little snake and the bird mean this. Okay, so now what, the little arrows that I draw on the molecules, they mean vibrations and how that impacts the infrared spectrum. So we do a lot of hieroglyphics in this class. The MOs with the red and the blue colors, that's like hieroglyphics. What is supposed to be meant by this red color? What about this blue color? The p orbitals, the d orbitals, the little donut in the middle, all of that stuff means something. And the character table helps us understand what that means. Okay. So this is the symmetries of molecular motions. Those would be the arrows. They help us determine the symmetries of molecular orbitals. And they help us determine the interactions of equivalent nuclei. So this applies to infrared spectroscopy through the molecular motions, UV spectroscopy, X-ray spectroscopy, visible spectroscopy in the molecular orbitals. That also allows us to understand bonding, because the molecular orbitals are, if you're making and breaking bonds, you're dealing with molecular orbitals. And then in NMR, we can understand the NMR signals because of the equivalent nuclei that we can get from the character tables. And the character tables come from the point group of the molecule. And the point group comes from the geometry of the molecule. And now finally we get to something you've heard of. Okay, the geometry of the molecule comes from the Lewis dot structure and the Vesper shapes. So in your Chem 1, when you got to bonding and the Vesper shapes and you did the Lewis dot structure and you started to make the molecule, that's what we're going to start with here. So we'll review all of those things with the Lewis dot structures and Vesper shapes. So that's the very basis of it. If you can draw those shapes accurately, maybe you can see the geometry and come up with the point group. And then once you get the point group, you just look up the character table and look up the direct product tables. So this first part down here at the bottom, this is where the difficult work is. It's trying to see the geometry and decide upon the point group. So up here, there's a link on the PDF version of your notes. This is a link to a GenChem textbook that's online. Because if you were, I would say, like I wasn't thinking ahead. Even though I was a chemistry major, I sold back my general chemistry textbook. Why did I do that? Okay, that was a close friend. I had marked in it. I had, I knew that such and such was on the left side of the page early in the book and everything, and then I threw that friend away for $20. That's pretty bad, So if you did that too, here's a nice online version of a GenChem textbook that you can go back and review the Vesper shapes. And so if we click that, if I switch over to turn on the browser. Okay, yeah, so let's go back now. Let's see. So you can come over here. There's a view online. Man, this is a great thing. No, I don't need pop-ups. Thank you. Okay. And so you've got all of the table of contents on the left here. You can go to chemical bonding and molecular geometry. Okay, Lewis symbols and structures. Oh, this is so great. Review how to do all your Lewis structures. It's all good. And then it'll get to the VSEPR theory, the valence shell electron pair repulsion theory. So I encourage you to go through and review these things. If you're weak in it, if you're strong in it, that's fine. You can go in and here we start getting the angles, and here are the shapes. Okay, so when they say regions of high electron density, I'm calling those electron domains. It's like areas where the electrons are around a central atom. And so if you have two electron domains, you have this spatial arrangement, and it's a linear structure. So this is the electron region geometry. Okay. Let's do water. So 4 regions of high electron density around that oxygen. And it has a tetrahedral electronic structure, but it's not a tetrahedral molecule. Okay? You only have 2 atoms around that oxygen atom, so it's a bent structure. So we call it a bent molecular structure. So that's one thing they don't really point out in this freshman level, is the 2 different, they kind of do, they say electron region geometry. Let's call that the electronic structure. And the molecular structure is where the atoms are. Okay, so I want y'all write that down. The electronic structure is how the domains are organized. Electronic structure. It's how the electron domains are organized. Electronic structure is where the electron domains, or how the electron domains are organized. but the molecular structure is where the atoms are. So we would use the atoms to decide on what we call the molecular structure. So water's bent. Okay. Sometimes they're the same, like in methane, like we see here. The electron domains around that carbon atom are tetrahedral. And the atoms around that carbon are all the same. And so the molecule structure is tetrahedral. But if I have chloroform, where I have one hydrogen and 3 chlorines, okay, then that's not a tetrahedral molecular structure. The electrons around the carbon are kind of in a tetrahedral arrangement, but we have to have another name for that chloroform molecule. It might be like a trigonal pyramid, but it's not a tetrahedron. Okay. So let's go back to our notes so I can write on those. Okay, so we start with the Lewis dot structure. We use those electron domains to determine the 3D electronic structure. I'm going to go ahead and put an arrow here, electron domains. Okay, and then I'll put the atoms. I'll give the molecular structure. Okay. And so then we use that 3D molecular structure to determine the point group for that molecule. So over here on the left, this is a Lewis dot structure, but we don't stop there. This is boo, hiss. Okay, because it's not 3D. It can't be realistic, right? This is a freshman Lewis dot structure, and it's correct as far as a Lewis dot structure goes, but it's not a VSEPR shape. You need to let it go 3D because we want to describe real molecules. You know, in this, the reason this is boo is this is a 90-degree angle, right? And that's not true. That's not accurate. But we let these go, in each of these carbons has a tetrahedral electronic structure, and so we know that these angles are 109.5. And that's more accurate. Okay. And so now we have staggered ethane. This is nothing. This is a Lewis dot structure, but it's nothing in relationship to reality. Okay. Except that the bonds are all there. Okay. But as far as the shape, when we're dealing with the shapes of molecules, when we're talking about symmetry, we need to be as accurate as possible. And that's why we need to draw these as accurately as possible. Right? It's not enough for you to draw this flat structure and then just put a wedge here and a dash there. I know some of you do that because I see it all of the time, right? You just draw this sort of freshman level Lewis dot structure and just put dashes and wedges there, but you still leave it to where it looks like 90 degrees. If you draw structures like I'm doing on the left, you're not going to see the symmetry. And that's going to hurt you. You're not going to be able to see it when everybody else is getting the answer like this. Once you see it, they're easy. But if you make your life difficult for yourself by drawing it like I'm drawing on the left, then you won't see it and you won't get the easy questions. And that's bad. You want to get the easy ones, right? So over here, we can see that these hydrogens are almost right on top of each other. So you draw them really close together, and then you draw the dash for the one in the back and the wedge for the one in front. And these hydrogens are right on top of each other. And so you have this dash for the one in the back and the wedge for the one in the front. And so you can kind of see that they're on top of each other. And you hopefully can see there's a threefold rotation axis right here. So if I rotate this 1/3 of a turn, this hydrogen comes up here and goes into that hydrogen. And this hydrogen goes to the one in the back, and this hydrogen comes to the one in the front. Can you see that threefold symmetry? The molecule can rotate 1/3 of a turn, and each hydrogen changes places. That is a symmetry element, a third of a rotation for this molecule. That's called a C3 axis. It's like 3 clicks. right? I can go hydrogen 1 to 2, hydrogen 2 to 3, hydrogen 3 back to 1. And I can click it 3 times and I'm back to where I was. That's how we know if a molecule has a symmetry element. If I had that molecule here and you closed your eyes and I rotated it and it said open your eyes, you couldn't tell I did anything, because all the atoms are in other places where there's an identical atom. Now this molecule over here is less symmetric than ethane. This is acetone. And we see this sp2 hybridization for this carbon. It has 3 electron domains. And so those are 120 degrees, those angles. Can you see the reflection plane in this molecule? So right down the middle, I'm going to kind of draw it like a mirror. So like a mirror. If you put a mirror there and you just saw the right half of the molecule, the reflection in the left in that mirror would give you the left hand of the half of the molecule. Okay. So it's important to draw these accurately, and that way you can see that there's a mirror plane or there's an inversion center and so on. Okay, so what is symmetry? We keep talking about something being more or less symmetric. So symmetry is defined by the number and types of symmetry operations that leave the object unchanged. So we do operations on these molecules like that rotation, and it leaves the molecule unchanged if the hydrogens have another hydrogen to rotate into, or the carbons can rotate into another carbon. So these atoms have to be the same atom or same element, and they rotate into similar elements. And that's when in NMR we're talking about equivalent nuclei. If you can exchange 2 hydrogens with a symmetry operation, then they're equivalent nuclei. So that's immediately one of the applications for this, is you can determine which atoms are equivalent. They have the same types of bonds to the same types of atoms and so on. So which is more symmetric? If this is the definition, we have a thing like an octahedron over here, which has 8 faces, 6 identical points. We have a tetrahedron here. We have some, square prisms. Here's a cube. Here's a cylinder. And so the number and types of symmetry operations. The reflection planes are let's try to think about this cylinder. Or let's start with this object here. Okay, so it's got a reflection plane here where the left and right can reflect into each other. It's got a reflection plane across the middle, so the top can reflect into the bottom. It's got a reflection plane here where the front can reflect into the back. It's got a rotation axis here. And that rotation axis is a C4 because I have 4 positions I can put that object in. Okay, but up here out of this one, it's just got like a C2 axis. I have to flip the thing all the way around 180 degrees for it to look like it did. Notice how this one has a C4 out the top, a C4 out the side, a C4 out the front. It's got some rotation axes that come out of the corners where this one doesn't. So the cube has more symmetry than this thing. What about this rotation axis coming out of this cylinder? It has an infinite rotation axis. So I can rotate it one infinitesimal degree, and it would still look the same, right? So it has an infinite number of positions. And so that's a number, right? It's not technically a number, but it's a magnitude of rotation axes. So a cylinder, something with a smooth angle here, has infinitely more rotation axes than the cube. So a cylinder is more symmetric than a cube. Well, the most symmetric thing in this list is this sphere, because it has an infinite number of reflections. It has an infinite number of rotation axes. It has an inversion center. It has all of these different kinds of symmetries. So that's what we mean by symmetry and ranking symmetries. The more symmetry elements it has, the more operations you can do on it to leave it unchanged, the more symmetric it is. And so here's our operations. This is wonderful. There's only 5, and one of them doesn't do anything. So with these 5 operations, you can classify all of the molecules. The E is identity, Cn is an n-fold rotation axis. Sigma is a mirror plane. We've already kind of used those. I is an inversion center, and S is called an improper rotation or a rotation reflection axis. So I'm going to write on here improper rotation. Now, and I wish they didn't use the word proper and improper, because that sounds like it's moral, right? It just, standard or non-standard. Why don't we say that? Yeah. So the CN is the proper rotation, and the SN is the improper rotation. So there's two types of rotations. Okay, but there's no moral component to it. These, just as an aside, these are not commutative. So it matters which order you do them in. It can, at least. And so here's all of the definitions in your notes, but let's go learn by doing, okay? So these are just there for you to refer back to, and we're going to go to this SymOtter webpage. Okay, so here we are at SymOtter. This was your tax dollars at work. They got a grant to create this webpage to teach symmetry. Okay, and because it was grant funded, now it's available for everybody. So props to Otterbein University and the NSF grant that they used. So here's the tutorial, the symmetry tutorial, and here's all of the different elements that we're going to look at. And so let's look at all of the ones in ethane, because we drew ethane earlier. So here's the ethane molecule. I'm going to tip it up. So you see the wedge and the dash. I've got those hydrogens right on top of each other. And let's look at some of the rotations. So here's the rotation axis out the top. That's called a C3 axis. You see the threefold symmetry? And I'm going to animate it. So this is the rotation around that axis. Isn't that cool? So you can come and play on this website. Now, this is a C3 to the -1 power. And to the -1 just means you go in the opposite direction. Okay, so C3 and C3 -1 are just in opposite directions. Okay. Let's do some C2s. Okay, this is crazy. All right, there's a C2 axis right here. It's kind of hard to see, but it's better when I rotate it. So let's go. See, now the carbons rotate into each other and the hydrogens rotate into each other. In fact, there's a whole bunch of C2s on this molecule. Let's look at this one. So that's going along a different 60-degree angle, and then this one. So a little difficult to see at this angle, so let's tip it up and we can kind of see which ones that they're going around. So this is one C2 there. You see it's kind of going up and down on our screen. This is that one that's going from the northeast to the southwest, or vice versa. Yeah, there we go. So do you understand proper rotation? Okay. Notice all the axes for rotation go through the center of mass. All the axes go through the center of mass. Okay. All right, let's turn those off. The center of mass itself in some molecules is an inversion center. So notice this hydrogen has a partner on the other side of the center of mass. And the carbon has a partner, another carbon atom. They have to be the same element on the other side of the center of mass. And so if I animate the inversion, watch what happens. The molecule goes right through the center of mass to the other side. So every atom goes through the center of mass to its partner on the other side. I'll do it again. So every atom goes through the center of mass to the opposite side of the molecule, the same distance away. And that's inversion. Now, my favorite is the improper rotation because it's so cool. Okay, this hydrogen is connected to this one down here, even though they're staggered, right? They're staggered, but this hydrogen can go to that hydrogen through the improper rotation. So you rotate it 1/6 of a turn and reflect it through. So it's two operations in one. You rotate and then reflect. Rotate 1/6 of a turn because it's an S6 axis. So that means 1/6 and then reflect it through. 1/6 and reflect it through. Now, if it's the opposite or -1, then you just go the other direction. So you rotate it the other direction 1/6 of a turn and reflect it through. So if I do this 6 times, the hydrogen goes down to the bottom, and then it rotates over and comes back to the top, and then it rotates again to the back and goes down, then it rotates to directly behind and comes back to the top, rotates one more 6, then comes down, and then rotates again and comes back to its original position. So if you do an S6 6 times, you get back to the original. All of the labels, if you were to label all the hydrogens, they would be back in their original positions. The same with a C3. C3 3 times, you've replaced all the labels back to their original place. Reflection planes, let's do those. Now there's no horizontal reflection plane, because if I were to reflect the molecule from the top down to the bottom, this hydrogen has nothing down there to reflect into. Okay. But it has some reflection planes left and right. So if I animate that, that's the left and the right side reflecting into each other. And then this one is kind of the back that way. I'll turn it this way so you can see. And then that one looks kind of like an orange. Okay, yeah. You see all the different reflection planes, and they all contain the center of mass, right? The center of mass is in all of the planes. The center of mass is in all of the axes, and the center of mass may or may not be the inversion center if it has one. So the center of mass is the point for the point group. So we talk about point group symmetry. It's the center of the molecule that's the point. So you kind of find the center of the molecule, and that's the origin. That's where 0, 0, 0 is. And then you're looking at positive X and negative X, positive Y and negative Y, positive Z and negative Z to see if they look the same. Okay, and if atoms of the same type can reflect into each other. So practice on SymOtter and enjoy the lab next week, and we'll be working with symmetry the whole next week. Okay.